Hello, welcome everybody. It's a pleasure for me to welcome you to our second Carbon Lunch. And thank you all for joining us to learn more about carbon capture and storage in the industrial and power sector. We're very happy because carbon capture and storage finally gains the spotlight it deserves. My name is Lee Beck. I'm Senior Advisor at the Global CCS Institute. The Global CCS Institute is an international think tank led by members including governments, companies, and nonprofits. We're currently represented in 7 countries, but were originally founded by the Australian government. We now work in the UNFCCC International Governance Mechanism, as well as with the largest emitters to accelerate the deployment of carbon capture within an energy transition that reduces emissions to zero by mid-century. However, Carbon Lunches actually is co-hosted by the Global CCS Institute, the Carbon Utilization Research Council, and industry group, which is led by Executive Director Shannon Andrelski, whom you're going to meet later, and the Carbon Capture Coalition, which is co-hosted by the Great Plains Institute and the Center for Climate and Energy Solutions. Unfortunately, the co-directors Brett Crabtree and Jeff Bobek couldn't be here today, but the Carbon Capture Coalition is a group of stakeholders that advocate for carbon capture and storage. These 3 groups came together earlier this year to develop this program, Carbon Lunches, which is a series of briefings to really do 3 things. 1, advocate on carbon capture and storage. 2, educate about carbon capture and storage and help people understand why it's an important climate solution. And 3, dispel any misperceptions that carbon capture and storage is an essential solution to the energy transition. We're very grateful for our supporters that include the Center for Climate and Energy Solutions, the Great Plains Institute, the Clean Air Task Force, ClearPath, the Bipartisan Policy Center, Third Way, and the Citizens for Responsible Energy Solutions. The first briefing we held a couple of weeks ago on March 28th, and we discussed the Intergovernmental Panel on Climate Change 1.5 degree report, as well as the International Energy Agency's Global Energy and CO2 report. And what became really clear is that while 2018 was the worst year in terms of emissions to date, carbon capture and storage is really needed as part of a raft of solutions to reduce emissions to zero by mid-century. What we also learned during that briefing is that with climate ambition increasing, so does the importance of carbon capture and storage. Why? Because if we're looking at limiting global warming to 2 degrees, for example, the International Energy Agency expects 14% of emissions reductions to come from CCS by 2040. However, if we're looking to go to zero emissions, increasing climate ambition, which is important if we're looking to limit global warming to 1.5 degrees and really confront the climate crisis, then the additional emissions reductions between a 2-degree scenario and a 1.5 degree scenario, 32% of reductions are going to be delivered by carbon capture and storage. So CCS is really important for getting us across the finish line to zero emissions by 2050. According to the International Energy Agency, and that's why we're also here today, 70% of investment in the energy transition will be either directly by governments or driven by government policy. Hence, we're looking to policymakers like yourself to help us formulate and implement policy solutions to accelerate carbon capture and storage in the energy transition. We're also very grateful for Representative Tahoe's office and the staff today for helping us preserve this really nice room. With that, I'm really excited and it's an honor for me to introduce today's keynote speaker, Jason Grumet, who's the president and founder of the Bipartisan Policy Center. Mr. Grumet is respected on both sides of the aisle for his innovative approach to improving government effectiveness and impacting public policy. Over the last decade, the Bipartisan Policy Center has combined the best ideas from both parties to promote health, security, and opportunity for all Americans. In 2001, Mr. Grumet founded and directed the National Commission on Energy Policy, which produced a comprehensive set of policy recommendations, many of which were incorporated into the 2005 Energy Policy Act. Mr. Grumet led the Northeast states for coordinated air use management, where he expanded the organization's technical and advocacy capabilities and its increased presence in national policy discussion. Mr. Grumet regularly authors commentaries and editorials in national publication, as well as participates in various broadcast interviews on major cable news. He frequently speaks at national forums and testifies in front of Congress. Thank you so much, Mr. Grumet.
Thank you, Lee. It's very nice to be here, see a lot of old friends and frankly a lot of new faces, which I think is exactly what this conversation needs. As Lee indicated, I run something called the Bipartisan Policy Center, which does make me a genetic optimist at this moment in American political history. But I think actually there's some reasons for optimism, even in the highly freighted energy and climate debate. I'm going to share some thoughts about that with you. Essentially, I think there are four really highly nuanced reasons why carbon capture, use, and storage are pretty critical. They're economic reality, engineering reality, ecological reality, and political reality. So I'm coming in with a soft sell. What I want to do is give you a little bit of a sense of what, how I unpack that, and then hopefully set up the rest of the discussion, which will probably be a little more anchored in technological insight. So economic reality. Last I checked, there were several $1 trillion of existing valuable infrastructure that power our economy. Most of it somehow connected to fossil fuels. And I think it is the economic might and dynamism that the United States of America brings to the world, which is going to really be essential to solving the challenge we have to transition to a low-carbon economy. And it would be really dumb to screw that up. You don't accelerate the future by messing up the present. And so I think that there is a rather growing recognition that we are going to be relying on fossil fuels in one way or another to power our economy for decades to come. And we have to do that consistent with the climate imperative. And so from an economic basis, I think the recognition that we have to find a way for fossil fuels to be part of the solution is something that we think is reasonably obvious. So engineering reality, and I never took an engineering class, so I'm going to speak about this for 2 sentences. And just as a setup for Ron, I've never met anybody who has suggested to me you can run a cement or steel plant on electricity. I think there are, regardless of what you think about the potential for CCUS on coal or the imperative for the future of natural gas, there are certainly aspects of the 21st century economy that are going to always have some aspect of fossil fuels involved, and again, I think that makes this something we need to be paying attention to. Maybe most important is the ecological reality. Lee mentioned the IPCC study, a recent IEA study. Some of you remember back in the last 18 months of the Obama administration, DOE produced something called a mid-century climate study. Every single one of these studies has 2 basic conclusions: that we need to essentially decarbonize the economy, getting down to a net zero emissions, and that we have to use every technology we know and several that we don't know yet to get there. We simply cannot achieve those kinds of ecological necessities based just on what we have in our toolkit, and we certainly are going to have to rely on decarbonizing the fossil fuel sector, advanced nuclear, direct air capture, and other ideas that we think are important and under development. And then finally, what I probably care about most is political reality, because the Bipartisan Policy Center is fundamentally committed to the notion that American democracy can still solve problems, and that pragmatic steps are there and available to unite what have been different views. And we now have an alignment between ecological and political reality. Because the political reality is, unless we broaden the energy and climate debate to consider both existing fuels and the breadth of solutions, we're not going to develop a political coalition that's going to be able to act in the time frame that's necessary. And unless we develop those solutions, we're not going to be able to develop solutions that achieve the ecological goals. So for the first time in quite a few years, there's actually a much better alignment in this discussion than we've, I think, seen for a while. One example of that is 45Q, which are the 2 numbers in 1 letter that now just become kind of code for this community. But I'm sure most of you are familiar with the significant success in creating meaningful tax incentives for CCUS, as well as early aspects of the infrastructure around direct air capture. So winning is fun, right? I mean, one of the problems we have in these buildings right now is there's not a lot of winning going on. It's actually kind of exhilarating to put deals together and make progress and build coalitions and build trust and create partnerships. And what we saw around 45Q was a coalition that had not existed before. And it's frankly the first actual achievement in the energy and climate debate in several years. And it has created, it's why we're here today. I can tell you that if it wasn't for 45Q, I don't think there'd be nearly as many people in this room. And in terms of the momentum it creates, we're seeing it all around us. You see now in the House Science Committee an effort to move forward with this fossil energy, we call it FERDA, but I guess it doesn't really exist yet, but some fossil energy research effort on the Senate side. Bipartisan support for the effects bill has just come forward. The next iteration of the Use It Act, which again is kind of building upon 45Q, has been introduced in the House and the Senate. These ideas are bringing together industry and the environmental community in a way that has not been apparent for the last several years. It's forcing hard conversations in both communities. We are involved in a number of conversations with carbon-intensive industries about what their role and obligations can be, about climate change. We're having conversations with most of the big environmental organizations about how they have to understand the role of fossil fuels going forward. So, we have shaken the system in a pretty constructive way. And I think that gives me optimism because democracy is a momentum sport. It's like college basketball. And this is a room that has the potential to build some of that momentum. So just kind of wrapping up the big picture, this is about technology inclusion, right? That is the metaphor that has changed the debate recently. That is the idea that has taken a lot of people who I think were opposed to action on climate and said, well, look, you know what? We're open to a serious discussion. And while there are still many voices arguing that climate's not a real issue and many voices saying that the answer is to eliminate fossil fuels in 8 or 10 years, they're loud, but there aren't nearly as many of them, right? The real conversation we're hearing both sides of the aisle is it's time for serious people to have a serious conversation. If you look at the letters that are being submitted by Republican members in the kind of aftermath of the Green New Deal, it's like, hey guys, let's have a real conversation, right? Enough denial about science, but we can't have denial about economics or engineering. Let's have a real grown-up discussion. And this, I think, really motivates that, which is the constructive way. And I'll just kind of end by saying, while the future's now, it doesn't exist by itself. We are going to have to work to create a really dynamic ecosystem for innovation. And technology doesn't scale itself, right? So I think once we have more confidence that there are real solutions here, I think you're going to see more openness to the kinds of complementary policy that's going to be necessary to bring those technologies forward at the scope and scale that we're going to need. And the insight is not a new one. The Bipartisan Policy Center about a decade ago, we created something called the American Energy Innovation Council, which is a group of about a dozen CEOs who have been making the basic drumbeat argument that we need to triple federal investment in energy R&D. And there was a lot of interest in that for a while. There wasn't a lot of interest in that for a while. And guess what? The band's back together, right? And we're having real discussions now with people who actually have pens that get to sign checks saying it's time to think about a real different kind of, pick your metaphor, moonshot, breakthrough Manhattan project for technology. And I think that the CCUS idea, both substantively, economically, and politically, is really the engine for a lot of that discussion. So I am delighted to see a full room on a sunny Friday afternoon in a windowless basement. It's like Vegas, right? There's no windows, there's no clocks. You can keep you here for hours. But it really is, I think, encouraging, and it's really just nice to see the folks behind this. And I will actually finally end with the reflection that one of the big problems with technology policy is we're kind of a fickle country. We get really excited about something for 3 years, then we get less excited about it, we have administrations change, and the arc of innovation requires a certain kind of dedication. And this is a shout out to CURC, because Shannon and I were just like 20 years, the Carbon Utilization Research Council has been actually talking about these discussions in substantive, evidence-based ways for 2 decades. And that has been the resilience and the consistency in this discussion while governments have been flipping back and forth. So I just really want to acknowledge and thank you for everything that you guys have done to get us here today. Thanks, everybody.
Jason, for that. And you just led me into thinking about the fact that it's really two things I really just want to point out before I introduce Neva. It's going to take sustained and what I call aggressive, but we might want to use a different term, policy support for carbon capture to have a similar success story in the near term, like wind and solar. And it can get there, and it will get there. And Neva's going to talk a little bit about some of the historical successes that we've had. So it's a good segue to that as well. And you underscored a really key point, I think that's important for everybody in this room to understand, which is carbon capture right now is a bipartisan effort. And it's a real near-term effort that can achieve really substantial momentum and then also success in the near term. I think that we can actually get real reductions with policies that are implemented through 45Q and others that are in consideration right now with effect, as you said, and the research and development that will complement all of that. So I think that this is one area where we can actually achieve and advance on climate policy together. So I just wanted to underscore that, and thank you for your keynote and your comments, Jason. So what I am really pleased to do right now is to introduce CURC member, the Electric Power Research Institute, and with Neva Espinosa. She's going to talk to us about carbon capture. A little bit of an education here, so I hope that you all came with your notebooks. She is the director in the generation sector at the Electric Power Research Institute, or as some of you know, EPRI. And Neva is responsible for advanced generation, renewable generation, and enabling technologies portfolio. And really what these areas focus on is research and development to enable tomorrow's power system to provide flexible, sustainable, and cost-effective power. Prior to joining EPRI in 2012, Neva had 10 years of operational and engineering experience in the power industry, so she brings a lot to this discussion. She spent her early career in plant operations and engineering at Knowles Atomic Power Lab and with Exelon and NRG, so she knows the industry really well. She has a Master's of Business Administration from Wake Forest and a Bachelor of Science degree in Mechanical Engineering, and she's a graduate of the Navy's Officer Nuclear Program and held a Senior Reactors Operator's License from the NRC, so that's really impressive. As a member of CURC, Neva and her colleagues at EPRI bring a wealth of experience that are critical to informing our technology policy efforts. And so I want to welcome you, Neva, and thank you for being here to discuss carbon capture today.
Well, good afternoon, everyone. I'm super excited to be here, so thank you guys for spending the afternoon with us. I think we're going to have a really good conversation. So a little bit about EPRI. How many people here are familiar with EPRI? Fantastic, that's a lot of hands. I'm glad to see that. So EPRI is a 501c3 nonprofit R&D organization that looks at end-to-end power. We represent our members represent over 90% of the power generated in the US today. We're also a global company, so about 30% of our funding comes from international members. In the generation sector, which specifically focuses on utility scale generation, coal, gas, fossil, renewable, across the board, we're about 30% funded by international communities. And in some programs, a lot of our coal programs, closer to 50% funded by international communities. So we definitely get a broad perspective globally in terms of what's going on with different technologies and how we can bring it back and improve the power industry today. So I thought to start, we would look a little bit at the power industry CO2, where it is as of 2017 statistics, talk about some of our successes before we get into some of the technical stuff. If I get too technical, pretend like you're in Vegas. I think that's a good plan. I really appreciated that, so we're going to go with that. So this will be no surprise to you in terms of what we're seeing in terms of the fuel switch in the U.S. in the past 10 years or so, right? So in 2017, about 30% of our power generation came from coal. About 30% or so also came from gas. 20% or so from renewables. Most of that is hydro, actually closer to 18% renewables. Most of that is hydro. The remainder of that, maybe 6% wind, 1.5% solar or so. And then a solid 20% in nuclear power. So if you look at CO2 emissions that come from the industrial sector alone, 68% of those emissions come from the power industry, right? Which is why we kind of have our whole thing just talking about power generation today. So for all industrial CO2, 68% come from power. Of that 68% that come from power, 69% of that come from coal. and the remainder comes from gas with other things here and there, right? So if you look at the amount of CO2 emitted in 2017 from coal and gas plants, 1,783 million metric tons of CO2. That's a lot. 1,783 million. That's a lot of zeros, right? Which came from about 1,300, 1,400 sites. 325 of those sites, which put out 69% of that, were coal, and about 1,200 or so of those sites were gas sites, right? So you can get a feel for how much more CO2 comes out of a coal asset than out of a gas asset, which is probably not a huge shock to anybody here today, right? So when you look at that, we can't just assume that we're not doing a good job, because actually we're doing quite an amazing job. If you look at CO2 emissions since 2005, although they have gone up, 36 different nations reduced their CO2 emissions, and the U.S. accounts for 44% of those net reductions. And 80% of those net reductions came from the electric power industry, right? So the net reductions that happened in CO2 since 2005, 35% of them were due to the electric power industry, and you can see the breakdown there for the other impacts. So we've had a lot of successes, and we've done a lot of great things. Now, what's led to this? A lot of things have led to this. Primarily, those CO2 reductions from 2005 were due to two things. One was efficiencies, and the other was fuel switch. Right? We've had a significant fuel switch since 2005 that's led to that. So let's start with a little recognition. Let's go back 20 years. Okay, this graph, you know, it's an engineering graph, I'm sorry, but it's not that hard to look at it if you think about it. So you have the blue line. The blue line is SO2 emitted in millions of tons. The green bars are CO2 emitted in billions of tons. So it looks like SO2 is bigger there. It's not. I just don't have a scale big enough to put it all in one graph, right? CO2 is significantly larger than SO2 there. But look what SO2 has done over the past 20 years. What has made that happen? It's not just fuel switching, FYI. It's technology, right? It's the technology that this industry has adopted that has made a remarkable change in some of the emissions that we have put out into the atmosphere, right? So SO2 reductions in the past few years have been 85%. CO2 reductions about 10%. Again, most of that is due to fuel switching, and that's with an overall increase of energy output of about 8%. So we can do this again. We can do what we did for SO2 with CO2 by partnering together, by doing the right R&D, and by putting the right engineering practices in place. So the easy question on that is, well, why don't we just do exactly what we did for SO2? It seems like it worked. Why don't you just go and kind of, chemicals, go put those things out together and make them work together. But unfortunately, it's not that easy, right? So why not use the same technology? Look how great it worked for SO2. If you look at, this is the 3-year mean wet sulfur deposition in the US, the one on the, left for you guys from 89 to 91, and the one on the right from 2009 to 2011. It's a visible change. You can actually see that. But there's some significant differences when it comes to SO2 and CO2, and it's in a matter of scale. Right, I said on that first slide, one color graph was in millions, the other color graph was in billions. Right, SO2 is 1,400 parts per million in flue gas, and flue gas is exhaust that comes out of power plants. We're going to get into that a bit here. CO2 is 140,000 parts per million. Right, so you're at a factor of, and that should have another 0 there so we can update those before we distribute them. The comma is not in the wrong place, it's missing a 0. So 140,000 parts per million. So when you look at a matter of scale, the sorbents we've used and the technologies we've used for SO2 in the past don't translate to CO2 because just the amount of surface area you need alone to do it doesn't equate. Right, and that's when we get into some of the challenges with CO2 capture and some of the technologies behind it. So, carbon capture technologies today. There's basically 3 buckets you could think of when you think of carbon capture technology for power generation today, right? Post-combustion, right, before you're producing power. after you're producing power, pre-combustion, before, and then oxy-fuel combustion, which if you think of it as advanced cycles, a different way to make power. We're gonna get into this in more detail, and it's gonna make a lot of sense, I think. So, bottom line though, is carbon capture technology is all about separation. How do you separate carbon from what it's attached to, if you will, right? And post-combustion, you're separating carbon and nitrogen. Pre-combustion, carbon and hydrogen, and oxy-fuel combustion, oxygen and nitrogen, right? And all of this, chemical equations. This all takes some certain amount of energy to do it, and it's quite a bit of energy to do it. So at the end of the day, what's going to make carbon capture technologies successful is minimizing cost, minimizing capital costs primarily, and minimizing energy costs, which come with efficiencies of the processes. So any one technology itself isn't inherently better than the other, right? They all work part of the laws of thermodynamics. It's how can we make these processes most efficient, and how can we reduce the equipment size and the engineering of them, and trading off the energy and capital costs to let economics determine what's actually going to win at the end of the day. So we need to talk about the 4 risks or the 4 realities in terms of what makes CCS something we want to go after, right? And a big part of that is the infrastructure we have on the ground today and the assets we have on the ground today. And by far, for a majority of the assets that are on the ground today, the technology that we focus on is post-combustion technology, right? So I'm going to spend a bit of time talking about what post-combustion technology means, how that impacts both coal and gas assets, before we get into some of the other technologies. Okay, so let's start by talking about a power plant. How many people in here have actually spent time in a power plant? Any? Great, that's fantastic. Okay, good. So, supercritical pulverized coal plant burns PRB. These are very simplified, very generalized prints here, right? So, how does this actually work, right? So, we have coal, we have air, we have fire, we combust it. That's all pretty straightforward. Let's say we put in 100 megawatts or so of fuel for the sake of the conversation, right? What comes out of that? We boil water, we get steam, it goes forward to a steam turbine, and we get about 38 megawatts on average out of a steam turbine putting in 100 megawatts in, about a 38% efficiency plant, right? You spend about 3 megawatts running the other equipment in the plant, right? I put like 3 components on there. There are thousands of components in a power plant, right? So 3 of those megawatts, 3% goes back to power all the things you need to power to generate that 38 megawatts. And then you have a bunch of exhaust that goes out, and that's where you get CO2 emissions. You get a lot more than CO2. You get oxygen, you get nitrogen, you get some argon, you get lots of stuff, right? But the CO2 emission for a typical coal power plant is about 0.775 tons of CO2 per megawatt hour. And then you have some other energy losses. You have condensate that goes back, and you have some recirc. But that's kind of the basic operation of a power plant. It's pretty simple, right? And that's a coal plant. It gets slightly more complicated when you look at a natural gas combined cycle plant, but it's relatively the same, right? So you have the same cycle here, right? If you think of the coal plant cycle you had over here, the steam cycle over here, you're just adding a gas cycle on the bottom. So on the bottom right-hand or left-hand part there, you see a gas turbine. So you have natural gas, you have air, and you have some ignition that sends power out of your gas turbine. So again, let's assume we put 100 megawatts of fuel into a combustion turbine. Right away, you get out 35 megawatts to the grid from your combustion turbine, okay? Then you take that exhaust gas that comes out of the combustion turbine, and you use that to heat water, just like you did in the boiler, in the steam cycle, right? So now you're heating water, which is sending steam forward to a steam turbine, and you're getting an additional 17 megawatts out of that, right? So now you have a 51 or so percent efficiency for the same amount of fuel input because of the combined cycle aspects of this plant, right? And then the other process is still generally the same. You have exhaust that's going to come out of your heat recovery steam generator, and that's going to put out some CO2 as well as other things in your flue gas. You'll see that the CO2 concentration here is much less for gas than it is for a coal plant. And then the same thing, you have recirculation of condensate and whatnot. So if you took like a count, and you can kind of see the pluses and minuses, what came in and what went out on the bottom left-hand side there, or right-hand side there for you guys. So pretty simple flows that end up happening for a natural gas plant, just like a coal plant. You'll also see a difference in the natural gas unit of this right here, this 1 megawatt of auxiliary power, right? So we talked about the amount of power it takes in a coal plant to run the plant itself. It's about a third of that for a natural gas plant. So there's less equipment, it's just a bit more simple. You don't have pulverizers, you don't have as many feed pumps, you don't have as many things as you do in a coal plant, not quite as much of the equipment to keep it running and operating. Okay, so these are the plants as they stand today. This is before we've added any kind of carbon capture technology onto them, and we'll get into that in a second. So when you talk about post-combustion carbon capture, there are really kind of 4 key technologies that are used. I'm not going to get into the details of these technologies. This is as far as we're going to get into these technologies, right? But they're good to know, right? We have absorption, adsorption, membranes, and cryogenics, right? Similar to, I said, post-combustion is what's mostly on the ground today. Absorption is mostly what's on the ground today for post-combustion capture, right? The one all the way on that side, using sorbents and amines and things like that. So fundamentally, the technologies used for post-combustion capture are the same for coal and gas, right? They're asset agnostic. They don't care whose flue gas they're cleaning. They're going to clean it. Right, and that's really important as we look at the investments we're making in this area, the R&D we're making in this area, to understand what's different and what's the same and how we can leverage those engineering decisions is really important as we make those investments. So again, there's no inherent energy advantage over one of these things versus another, because it really comes down to, can you separate them efficiently with low capital cost? Okay, so where do they go on a power plant, right? Because that's where the capital cost comes in. Okay, so in the field today, you have flue gas that comes in. It goes to some kind of, doesn't work on that screen, some kind of CO2 technology, right? That's showing an absorbent technology. You have flue gas out where the CO2 is removed, and then you have CO2 going out in a different place. What's important to look at here, and what's not shown, I'm going to show you in a second, are all the other things that have to interact with this system that add additional cost. And we need to get that cost reduced. You have to have steam in and out, right? You have some heating capability. You need to have power in and out, right? So that auxiliary power I talked about with the power plants, where the coal plant was 38% efficient and the gas plant was 51% efficient, you need to steal some of that power and send it here. And water. You need water for cooling capability, right? So all resources that impact efficiency and add cost to these plants that we really need to better understand and better optimize. So now let's take this and put it on a plant. And for the sake of simplicity, for the slide having room to put stuff, we're going to put it on a coal plant, okay? What's not shown on this for the simplicity of it is all of the environmental controls that are currently on coal plants today. And everyone's a little different, right? But generally, over the past X amount of years, we've installed SCRs, we've installed DSPs, we've installed FGDs or scrubbers, right? We're taking out NOx, we're taking out ash, we're taking out SOx, which, excuse me, leads to that graph I showed you guys in the very beginning, right? That's how we've gotten there. So post-combustion, that gets added after all that. That's where it goes, right there. Okay? Now when you do that, you need to make some changes to your FGD. That takes some cost. When you do that, you need to have changes. You have to pull steam from your steam turbine up into your post-combustion capture system, which means you have to make investments on that steam turbine, and you're taking some efficiency away from that steam turbine, right? So when you look at the theoretical idea of how much energy it will take you in order to do this, how much energy you need to steal from this plant, if you will, right? Just like that aux power. Theoretically, based on the amount of capture you have, if you're looking at doing 50% carbon capture, 1.47 megawatts. 100% carbon capture, 3.79 megawatts. You'll see it is a non-exponential growth, right? So the more capture you take, it doesn't cost you tons and tons and tons more. Right, but most things are designed today, when we talk about it, we typically talk in the 90% capture range. So you're talking about 3 megawatts, theoretically, at a 100 megawatt system to capture that CO2. In reality, we expect it to be about 4 times that. right? And that's what we've seen to date. So now you're talking 12 megawatts off of that 38 megawatt plant, right? And that doesn't necessarily include some of the losses you're going to have when you go and you make changes to that steam turbine, right? So this just shows you a typical steam turbine that may be in the field today. This is part of the LP and IP, low pressure and intermediate pressure parts of the steam turbine. And this is the area where you actually have to make a tie-in. So steam turbine looks small in this picture, but most of you have been in plants, you know the steam turbine is not small at all. It's very, very large, right? I had a picture here and for a while of me standing next to a steam turbine, but I deleted it. I can email it to you guys if you want to see it. Okay, so that's the area that you actually tie into the steam turbine, right? So and what I don't capture here is water, right? So you're using more water, you're tying into your steam turbine, so you're taking some losses there, and you're also taking some of your auxiliary power and adding some more auxiliary power for this technology, right? That being said, you're leveraging an asset that's on the ground today. You don't need the capital cost of rebuilding that asset, and there's lots of value in doing it. So I'm not going to draw this for a gas plant. So what are the core similarities and differences between a coal unit and a gas unit, right? Why do we care? What do we look at for R&D? Well, for a coal unit, you got your flue gas, it has contaminants. CO2 is about 12 to 15% and 14% of the flue gas, okay? The natural gas unit, much lower CO2 content. That sounds like a good thing, except it makes it actually harder to pull the CO2 out, right? Because there's less of it in there, so it's harder to find. So it actually takes significantly more energy the lower amount of lower concentration of CO2 you have in your flue gas. Which is why when we'll talk about some of the technologies in a little while, it's how can we separate the CO2 so it's in higher concentrations so we can strip it out of there, okay? And then for natural gas units, there's also other things like you could potentially use some of that CO2 cycling back into the gas turbine to try to up that concentration. So that's kind of a unique aspect of natural gas that we could potentially be looking into. But really what it comes down to at the end of the day is there is significant overlap between adding this technology to coal or gas, right? Which is great news because all the work we're doing goes twice as far. Okay, but separation processes, they're the same, right? We talked about the 4 technologies, they're the same for coal or gas. The amount of energy required, the amount of capital costs required, the power plant integration, right? The power plant integration can't be ignored because it's rather complex, right? So you're going to change the way you operate these units. Power plants today, the importance of them being flexible, having the ability to load follow, not only just follow load, but shift up and down relatively quickly to respond to change on the grid based on just the changes of what's on the grid today and a lot of our intermittent power sources. That's a challenge. It's even a challenge today with our existing environmental control equipment, which many times limits that flexibility. So all of the R&D and all of the work around those things to make this a reality is fully translatable to both types of assets. Okay. So technology is essentially asset agnostic. So post-combustion capture on power plants today. Right? We see 2 things out here today. I'm not going to go into this because I believe you guys are going to hear about this in one of your future briefings. But what I really want to point out here is the size of the capture technologies. So let's take a look at this one over here, the Boundary Dam facility. Boundary Dam facility is up in Canada. It's run by SAS Power. Okay, you'll see here in the slides it says 139 megawatt emitted net out of 730 megawatt coal. Right, so that's telling you that the capture technology for, I think there's 4 coal units at that site, I believe. Right, one of those coal units is 730 megawatts, and we're capturing 139 megawatts of CO2 emitted, if you will. So we're capturing from basically less than half one of those coal units. When I talk about capital cost, this is the capture facility. Right? So that's a lot, there's a lot of build, it's a lot of capital costs to capture less than half of the CO2 emitted from one of those coal units. This is why we need to do R&D, right? This is why we need to better understand the technology. because doing that allows us to get those capital costs down. And again, I said it's between energy and capital costs. How do you reduce both of those things? I'm not going to go through all the other pieces on that slide, but I'm sure Shannon said, well, you'll talk about it in a future briefing, and I'm happy to chat about it with you guys at some later day. So, carbon capture technologies today, right? Going back to the slide we started with. So we said we had post-combustion, we just kind of discussed that. Pre-combustion and oxy-fuel. Let's get into these next two technologies kind of together, because they're kind of complicated and they're advanced cycles. We're not going to go too far in the weeds on them, but we'll start with pre-combustion. And we see this in IGCC facilities. There's IGCC facilities out there today. There's one in the U.S. currently operating. There was another in the U.S. that was capturing carbon that's not running right now. Okay, but when you look at an IGCC plant, the difference is you are doing separation before you combust anything, right? So we are trying to separate CO2 and hydrogen on IGCC units. And we do that with an air separation unit and a gasifier, right? So just like I showed the other assets earlier, you start with air, you start with some kind of fuel, in this case coal, right? Before you put those two things together into any kind of power to combust it, you're going to take the air and you're going to separate oxygen from it, right? And that oxygen is going to go with your coal, and your coal is actually treated before it goes into this gasifier, which will give you a syngas, right? A syngas, in this case, has a lot of sulfur in it, so it has to go through some technologies, a cooler, and that sulfur gets removed and it takes the SO2 out, and then you have a clean syngas that goes to your gas turbine, and then that whole cycle is really no different than the cycle we talked about earlier, right? But the difference is the CO2 is in a much higher concentration, and therefore it's easier to get out of the air, because we talked about if there's more of it, you can find it more easily, it takes less energy to pull it out from where it is, right? So that's kind of the fundamental pieces around IGCC. There could be some high capital costs there, and there's a lot of complexities with it, right? It's a big chemical. A lot of people think of some of these technologies as large chemical plants, right? If you come out of the power industry, for sure, even the investments that we've made in terms of SOx and NOx and ash and whatnot, people look at that as large kind of chemical plants that are in the back end of their power plants. And that's going to continue, right? Because these are the technologies we use to pull these things out of the air, out of the flue gas. So that's a little bit about IGCC. Let's move on. Oh, actually, you know what? I didn't tell you about the carbon capture piece of it. So that's the IGCC plant on its own. Okay. Now, when you add carbon capture into it, you actually add another reaction. So there's some more modules in here where you have another reaction, and you pull the CO2 out super early. Right, so it's higher concentration CO2, and you pull it out where you pull out the sulfur, so you can take that and do other things with it, whether you want to sequester it, utilize it, advanced oil recovery, whatever it needs. All right, let's move on now to oxy-fuel combustion. All right, so what I did is this little picture is the same picture we used before with a typical coal plant, okay? And let's just slowly step through the differences between this plant, an existing coal unit, and what oxy-fuel combustion really does. Simplified. Okay, so what we've talked about so far, we have air, we have coal, we ignite it, we get some steam, that creates power, we get some flue gas, and that puts out some CO2 and other things. 12 to 15% volume of CO2 comes out of that flue gas. Okay, so with oxy-fuel combustion, you are trying to separate oxygen and nitrogen. Again, all in an attempt to get a higher CO2 concentration. So how do we do that? Okay, we do that by separating air. Okay, so with oxy-fuel combustion, you add an air separating unit on the front end of this, and you separate nitrogen and oxygen. Right? This is actually pretty expensive to do. It takes a lot of energy to do. Okay, oxygen and fuel is then mixed. And it's a pretty typical power plant from there. You have oxygen and fuel that's mixed. Again, steam goes off and sends power. Your flue gas now has closer to 80% volume CO2, much, much easier to catch. You have a CO2 purification unit, and you can pull the CO2 out that way. Okay? The problem with that is it runs really, really, really hot. right? So because of that, there's been another step which adds some capital cost here in terms of recycling that flue gas to minimize those temperatures, right? So the basis of oxy-fuel combustion is really utilizing cleaner air, if you will, just oxygen for that combustion, so you get higher concentrations of CO2 and you can pull out that CO2 easier, right? Because we said the higher the concentration of CO2, the easier it is to pull out, the lower capital cost, the less energy it takes. Okay? Now there's been a lot of excitement and a lot of conversation recently about the almond cycle. How many people are familiar with this cycle? A couple people. So what's really exciting about this cycle is it uses supercritical CO2 as the working fluid, right? So we've been talking about using steam as working fluid, we've been talking about using gas as working fluid, right? This cycle has kind of wiped away everything we've done in the past and looked at how can we most simplify the capital costs in here, reduce the amount of equipment, and use the CO2 to create energy, right? So you start off with it with an air separation unit, just like we did on the oxy cycles, right? Where you are taking out your oxygen, and you start this process with oxygen and natural gas, right? And your combustor goes up to a gas turbine, just like it did. But in this place, and you see the heat exchanger we drew a little big, this is actually called a recuperator, but heat exchanger just exchanges heat in a different way. What this actually does is it takes the CO2, it sends it back through into the combustor. So now instead of using oxygen to combust with natural gas, you're using CO2 to do it, right? And we said creating oxygen out of air is a pretty expensive proposition to do, right? So this cycle allows us to use a majority of the CO2 back in the cycle, create power, and then you still have some CO2 you can recover. You can either we can do whatever you want with it. You can use it for EOR, you can sequester it, whatever you may need to do. So a lot of really exciting things around the alum cycle. This is something that could potentially be a game changer. There's a lot of people that are making investment in it, and something that we're watching closely at EPRI, and I'm sure you guys are too, to see how this plays out over the next couple of years or so. Okay. So when you look at investments made, and this is a lot of what we do at EPRI, right? We're a research and development organization, and you look at the different TRL levels that are out there. It takes quite some time to get from something that's a basic research, just an idea, to full commercial scale. There are these technologies are out there full commercial scale today, right? They need to be improved for sure, and there's a lot of new technologies and new advancements that are being made, right? But the sooner we start, the way better we are. We are already very, very, very far down that path, right? We have lots of examples of basic research where we do modeling and we try to understand all the different types of technologies and amines and chemical developments that can be within a given capture technology that can be put on plants today. We have a huge amount of smaller pilot projects around the world that are looking at different capture technologies. And then we have quite a large amount of larger scale demonstrations around the world also where we continue to make strides in capture and try to get further and further along to get as many of these things in development as we can. And in addition to what was talked about earlier, what we're seeing in the power industry is a lot of our members specifically are a lot more interested in this technology over the past couple of years than they have been maybe a while ago, right? So we've just, over the past couple of weeks, matter of fact, we've gotten a lot of calls from members really excited and really looking to make some investment in these areas and figuring out how they can be a leader in capture technology. So really actually exciting time for us at EPRI, exciting time in the industry, exciting time for the country to see how this helps lead us to our CO2 future. So just some closing thoughts as I close out here. So CCS is a pathway to the energy future, right? It'll play a vital role. It already plays a role today, but it'll continue to play a vital role going forward, right? A diverse energy future is a great place for us to be. The technologies are asset agnostic, right? It can be leveraged for both coal and both gas. I think that's a really important thing to understand and appreciate as we make investments here. But it's going to come down to optimal economics, right? The technologies at the end of the day that are going to win are the technologies that will increase the process efficiency and that are going to reduce the equipment size. Because as you saw in the pictures, it takes a lot of equipment. It's really big to capture some of this CO2. The smaller we can make it, the more efficient we can make it, the better off we're going to be. And then collaboration and R&D needs, right? Bipartisan is a huge part of it. From the R&D side, though, doesn't just take any one type of engineer. It takes all of them. It takes mechanical engineers and chemical engineers and power engineers and geoscientists. I mean, it is across the board. All the players need to be part of the conversation and part of the process of taking us to the future with CCS. So with that, I don't know if I went over my time here, but any questions, or we'll do that later? I'm sorry? We'll hold the questions. So thank you for your time here. I appreciate it.
Thank you, Neva, so much. I think this was a really fantastic presentation. So now we're going to move to the other big sector of emissions, and that's the industrial sector. And with that, I'm really honored to introduce a former Global CCS Institute employee. He used to serve as our global lead for carbon capture technology. And now he's the principal, Ron Munson is the principal and founder of Cogenta Solutions, a consulting organization focused on developing customized, actionable solutions in carbon, energy, and environmental managing. Ron was formerly a senior engineer at contracting to the National Energy and Technology Laboratory at NETL in the U.S. Department of Energy, which you all know. At NETL, Ron supported greenhouse gas emissions mitigation research, development, and demonstration programs. This included support for DOE's programs all along the commercialization pathways from process concept through demonstration. He's also a chemical engineer. And yes, so we're going to look into industrial applications right now. Thank you so much.
Well, thank you, Lee. I appreciate it. Appreciate Lee and Shannon and Mike for helping put this together today. I heard that, I wasn't here for the last briefing, but it was about a month ago, but I heard that the inducement that Shannon offered to bring people into this briefing was lots of process flow diagrams. So the fact that there are as many of you here as are here, I'm really impressed and I really appreciate it. Let's go ahead and get started. Lee mentioned that Cogenta Solutions consults in a lot of different areas around carbon management. Carbon capture, of course, but also carbon utilization and reuse. And I help DOE with their research programs and with project development efforts as well. So there's going to be some overlap in my presentation and in Neva's, but hopefully that just helps to reinforce some of the concepts that we're trying to get across here today. You know, if you look at the International Energy Agency's projections as far as what's going to be necessary to meet different targets, different greenhouse gas emission reduction targets. Neva mentioned before that for the 2 degree C scenario, or maybe somebody else mentioned this, but that about 15% of the emission reductions associated with that scenario are going to need to come from CCS. And of that 15%, or of that emission reduction associated with CCS, it's split among the power sector and the industrial sector. And so globally, power accounts for about 40% of total emissions. The industrial sector accounts for about 20 to 25% of emissions. In terms of the amount of CO2 emission reduction that will come from CCS, it's really split fairly evenly. There's a little bit more that's projected to come from power production. So just over 50%, just under 50% is projected to come from industrial sources in the 2 degree C scenario. The other interesting part of this is that if you look at the more stringent scenario that they've evaluated, looking at the much less than 2 degree scenario, a lot of the additional emission reductions are going to need to come from CCS. And if you look out at the 2060 time frame, about half of the emission reductions in that time frame are going to be associated with CCS. So it's clearly something that we need to think about. Now, Neva kind of started this discussion talking about the importance of concentration of the CO2 in a gas stream, and the importance that has in terms of being able to remove that CO2 from the gas stream. And so I put together right? That doesn't work very well. Okay. I put together a little explanation of how that works. And so if you think about gases and start with gases in a box, in this top left box over here, and say you have nitrogen represented by the blue dots and CO2 represented by the green dots, and in the box you have a divider, and so you're keeping them separate. If you remove that divider, the gases are going to spontaneously mix together, and that produces entropy, it produces disorder, and so you lose some energy associated with that. The gas separation process is reversing that. It's taking that mixed gas and separating it back into its components, and it takes energy to do that. And that's a real important part of what we're trying to get at with CO2 separation. This plot over here on your right shows how that energy is required as you get to lower and lower concentrations of CO2. And you can talk about this as well. And the interesting part is that as you get to the lowest concentrations, the energy required goes up really quickly. And that impacts the cost associated with CO2 separation. So, it's important because there are a lot of different sources out there, and the concentrations associated with those different sources vary considerably. And so in the air, we're talking about 400 ppm, about 0.04%. Really low concentration in the air. It's going to take a lot of energy to separate the CO2 out of the air. In gas-fired power production and coal-fired power production, the concentrations are about 4% in gas-fired power production, 11 to 15% in coal-fired power production, still relatively low. Sectors like cement and steel have slightly higher concentrations. Cement on the order of 22%, steel's a little bit more than that, but in the same ballpark. So slightly higher concentrations. Then you start looking at some of the other industrial sectors out there producing different products, like ethanol or ammonia or natural gas processing. What you see there is really high concentration gas streams. And so, again, going back to this principle of the cost increasing as the concentration decreases, for these sectors with the high CO2 concentrations, the costs are going to be lower. So if we think about how that has played out in the real world so far, this is a diagram from the Global CCS Institute's status report. It shows kind of the history and the future of large-scale carbon capture facilities globally. And there are a couple of interesting things to note here. The dotted lines moving across the plot represent the different sectors where these facilities are operating. And the thing that jumps out most there is that there are a lot of them associated with natural gas processing. The blue dot, the light blue dots represent facilities that use their CO2 for enhanced oil recovery. The dark blue dots represent saline storage. Okay? But a lot of facilities associated with natural gas processing, a few others with some of the other process industries as well. The power sector facilities that are in operation, that Nico pointed out earlier, are the Petronova facility and the Boundary Gap facility up in Canada. Those are much lower concentration, and so they're going to be more expensive to capture the CO2. These top two are kind of interesting. They represent sectors that have not been active in carbon capture before, but one of them is cement, and the other is waste incineration. Those are both in Norway, and they're both undergoing FEED studies at the moment and are expected to move forward soon. But again, those sectors represent low concentration sources. So, what we've been taught by what has actually happened so far is that the sources that have high concentrations are the ones that dominate the operating facilities that are out there right now. And so things like ethanol production, ammonia production, natural gas processing, high concentrations, lower cost of capture. The lower concentration sources have far fewer facilities because their costs are significantly higher. And the facilities that have gone forward in those sectors have required a substantial amount of public support. So what does that mean in terms of actual costs? A report was put together about a year and a half ago, that looks at the costs associated with these different sectors. And again, these high concentration sectors have relatively low capture costs on the order of $20 per ton. In this graphic, I'm showing both the first-of-a-kind cost and the nth-of-a-kind costs, and that's a significant factor as well. Anytime you do something for the first time, it's harder. You make a lot of mistakes in the planning process. You build in lots of redundancies so that, if something goes wrong, you've got a backup system to take care of it. Those first-of-a-kind costs are always significantly higher than after you've built the 5th or 6th facility that is using a particular technology. And so the difference between the green bars and the gray bars is a representation of that difference in cost associated with a first-of-a-kind versus an nth-of-a-kind facility. The other interesting piece of this is that these are all based on modeling studies, and I'm a former modeler and have a great appreciation for that. But what we've seen on the ground is that the differences are actually substantially larger than that for going from first-of-a-kind to nth-of-a-kind. So, what are the technologies that are out there being used? And you did a great job of starting us down this road, and so I'll just kind of run through it quickly, and in the context of different concentration sources. But there are solvent technologies, sorbent technologies, and membrane technologies that are out there being used at scale right now. For both the solvent and sorbent technologies, they kind of operate on similar principles. It's just that the solvents use a liquid to grab the CO2. The sorbents use a solid to grab the CO2. So the CO2 ends up being associated with solid particulates for the most part. There are a couple of different mechanisms that are important in removing the CO2 from a gas stream. And so there's physical mechanisms, so physisorption, and that's just kind of a weak association between the CO2 and the capture medium, the sorbent or the solvent. And those kinds of approaches are really good for high concentration gas streams. But if you have the lower concentration gas streams, like we see in power production, in cement and steel, you need something that is actually going to go out there and really grab that CO2. And that's a chemisorption approach. And so it actually forms chemical bonds between the CO2 and the solvent or sorbent mixture, that you're using. And so one of the challenges there is that when you've made those chemical bonds, you have to work harder to break those chemical bonds. And so it requires even more energy. The other approach that is being pursued is membrane-based capture. Membranes operate by exposing your feed gas to a membrane surface, and that surface is specially designed to allow one component to move through fairly quickly while the other one does not, and so you get gas separation based on that. Again, as Neva mentioned, the vast majority of the facilities that are out there operating right now use solvent-based systems. There's one large-scale facility operating down in Port Arthur, Texas, that uses a sorbent-based system. It's a hydrogen production facility. And then there's also one membrane-based capture system that's being used in natural gas separation at Lula in Brazil. Okay. So these next few slides, I kind of want to go through and look at some of these specific industrial applications to kind of reinforce what I've been talking about in terms of the cost and the ease of capture in these different systems. And it helps explain why these systems offer a real opportunity moving forward for carbon capture, and why they've been the ones that have dominated the facilities that have been produced so far. So, one of the sectors that we talk about is natural gas processing. Whenever you extract natural gas from the ground, it doesn't just come up as a pure system. It always has other stuff in it. Some of the other stuff often includes CO2. And so if you want to sell that natural gas and put it into a pipeline, you have to remove that other stuff before you can do that. And so it's just a natural, everyday part of doing business for them to remove the CO2 as part of the natural gas processing industry. And so you end up with a gas stream that's very high concentration, pretty high pressure too. And so it's inexpensive to go ahead and put that into a pipeline and send it for storage or use. Fertilizer production is a similar type of thing. It's, again, just kind of a natural part of doing business in the fertilizer or ammonia production industry. And so, you start out with your fossil fuel, usually natural gas in this case. You reform that to form syngas, which is mostly carbon monoxide and hydrogen. You shift that syngas, so you convert most of that carbon monoxide into carbon dioxide and more hydrogen. And at that point, you can separate out the CO2. They have to do that in ammonia production because this next step involves a catalyst that would be poisoned by the CO2. So again, they have to remove the CO2 in this process. Now, a lot of times what they'll do is they'll take that CO2 that they've taken out of it, move it over, pipe it over to another production unit to generate urea. But if there's excess CO2, then that can be compressed and then sold. And that's done at a couple of facilities in the Midwest, in Kansas and Oklahoma. Ethanol production is another interesting one. You'd start out with some kind of biomass, corn, sugar, or something like that. You grind it up, process it, get it into a form that you can deal with, and then you send it for fermentation. The fermentation process generates a almost pure stream of CO2 coming out of it. And so, it's about 99% pure. The only thing you need to do with that in order to transport it or for use or for storage is to take the water out and compress it. And so, again, it's a very low-cost opportunity to separate CO2. And again, you see several facilities that are doing that. They're not all at the same scale as the processes that we're talking about. That's another common feature of industrial separation, is that they're often not at the same volumes that you'd see associated with power production, but you still need to get at it somehow. Hydrogen's an interesting opportunity as well. Hydrogen is something that has received a lot of attention in Europe, a lot of attention in Asia as well. So production of hydrogen with CCS hasn't received as much attention here, but I think it deserves more attention. It's the same process as you start out with in ammonia. Typically you start with natural gas, reform that, form syngas, treat that syngas to generate more CO2, and then you can take that CO2 out of the system using techniques. It's at high concentration, and you can use techniques that don't require a lot of energy. And so it's a low-cost opportunity. There are other CO2 sources within a hydrogen production process and other places where you can remove the CO2. But this one, the syngas, offers the lowest cost opportunity, and it still gets you nearly 60% of the CO2 that's generated in a hydrogen production process. So if you were building a facility, wanted to be able to remove a significant portion of the CO2 generated, that's where you'd start. The last sector I want to look at in a closer way today is the cement sector. And Jason mentioned this earlier. There's no way to electrify your way out of CO2 production in the cement sector. And that's because one of the key processes associated with cement production is this process where you take calcium carbonate heat it up to drive off the CO2, and you produce calcium oxide. You know, that CO2 that's produced out of that process is going to be produced if you're going to make cement, and so you absolutely have to do it. The only way to mitigate that is to capture that CO2. Now, the way most cement plants operate now is all of the waste gases that are generated in the process are all combined together and sent up through a stack at the end of the plant. And at that point, the concentration of the mixed gas stream is 20–25%. There's a real opportunity, though, with this process to kind of separate out that calcium carbonate to calcium oxide production process and capture the CO2 that's generated there while it's at the high concentration. And there's a pilot facility that's operating in Belgium right now where they're doing exactly that. And so I think that there, again, is a significant opportunity to reduce emissions from cement production. You won't catch all of the CO2 by doing that, but you get about 40 to 50% of the CO2 that's associated with cement production. And so, you know, just to summarize quickly, you know, there are really significant opportunities in these different high concentration sectors to move CCS forward. And so they're inexpensive, you know, relatively inexpensive, and incentives are in place just with 45Q that might help move operators toward pursuing CCS. I think they need a little bit more in terms of incentives, but in terms of the cost of capture, they're low enough that there is a real opportunity there. The costs in the other sectors, the low concentration sectors like power, like steel production, they're higher, and they're still a significant barrier to deployment. But there is research and development that's going on now to lower those costs. A lot of the research that is being done for the power sector could be transferable to these other sectors as well that might help drive down those costs. And like I said, you know, incentives and policy actions are a critical component of driving this whole thing forward. And so that needs to be a major part of what we're talking about and what we do moving forward. With that, I kind of ran through it quickly, but hopefully there's some explanation there, and if you have questions, I'm happy to answer those.
Yes. So thank you very much, Ron. And I'll invite you to ask any questions. Steve, please also feel free to come up front. Ask away, since we helped them since the beginning. So.
Question for Ron on that last slide. Do you see if there's higher uptake of this high concentration of removal, do you see benefits spilling over into the lower concentration, or are they using similar technologies?
The technologies, the actual separation technologies are typically a little different because you can use technologies to get at these higher concentration gas streams that don't do a good job of grabbing the CO2 out of lower concentration gas streams. Where there is a benefit, though, is kind of the associated infrastructure that would go along with it. So, for instance, if you started getting CO2 from a lot of these industrial facilities that need something to do with it, you need pipelines or some way to transport that CO2 to its ultimate use, whether it's enhanced oil recovery, storage, whatever it is. So there are kind of these ancillary benefits that are really important, but from a technological standpoint, they're going to be different.
For ethanol, you mentioned the costs are still around $20 a ton, and that's mainly from dehydration and compression. Is it the same also for ammonia and production and natural gas processing? Is it the same to dehydration and compression? And then are there opportunities to reduce those costs further?
So the costs are similar in those different sectors, associated exactly with what you say with dehydration and compression. You know, there probably are some opportunities. One of the things that NETL has been working on for several years, probably with different involvement, is the development of compression equipment that is more efficient and more effective. And so that's has potential for some real cost reduction. And I think that technology is either now or has just finished being tested. It's gone through several corporate changes in terms of who's doing it, but I think it's Dresser Rand that owns the company that is pursuing that. Grant.
These projects usually on company balance sheets or financed through special purpose vehicles?
That's a good question. Yeah. So the recent projects, and especially those in the lower concentration sectors, actually you correct me when I'm wrong, please. So the recent lower concentration projects all had some significant public financing, and probably would not have moved forward. In fact, if you talk to the principals involved, they said the public financing was an essential element of them moving forward with those projects. The earlier ones, there are projects, EOR associated projects that started in the 70s and have been operating ever since then, using typically natural gas processing, CO2 from natural gas processing. Those are money makers and have been for a long time. And they started because they saw an opportunity to make money out of using that CO2.
I would agree with all that. I would say that we are starting to see the power industry side players that have not necessarily been interested in the past to make any investment from their own balance sheet, starting to make investment, but only through joint venture ventures or public funding, government funding, things like that.
How much of an effect would a federal carbon tax have on the economic or the commercial viability of these technologies?
I'll let you go.
Yeah, I don't really have an answer for you on that, to be honest with you. So I could go back and see what models we have, but I don't have an answer on that.
The one thing that you can say is that if you really want to get this moving forward, you need incentives of some kind, right? And that's an example of what type of incentive that might go into it.
Can you talk a little bit about the existing commercial products for carbon capture technologies today for power plants?
Sure. Well, so there's a lot out there, right? So we've done a lot of work at EPRI that analyzes. We have analysis over 250 different solvents that are out there today. We have a lot of models that we have built internally in-house that looks at them to really understand the proprietary nature of them, what kind of chemical composition, how they break things down, what the reactions look like, what type of energy is required. And different companies have different proprietary solutions around the world, right? So even understanding that modeling of it, right? Modeling of thermodynamics is relatively easy. There's software that does it. But understanding what those reactions are that go into that modeling is actually quite complex. So understanding how a different given technology or a different given solvent will actually behave for a system, how the system's designed, it's pretty complicated. But if you're interested in learning more about it, I could show you our website that we have that has lots of different information on.
It's with regard to the vendors or the number of companies providing these technologies. Can you give us some insights here?
Well, so like I said, there's over 250 different solvents out there today. We don't necessarily do vendor evaluation or say this one's positive, this one's benefit. EPRI does not do any type of lobbying or advocating for one company or another. We just do have objective evaluation of how those solvents behave. And like I said, I have a website I can share with you if you can see that's what it looks like.
If you just look at the commercial facilities in power, there's just two, right? And it's Mitsubishi, not one of them can't solve the other, but there are a lot of companies
That's right.
developing solvent and other types of technologies that I think have a lot of opportunity to move forward. And most of those are still at the pilot demonstration scale. So it's not tomorrow, but they're coming.
You guys both talked about the importance of getting the cost out of removing the carbon. I guess the flip side of that coin is to find a more valuable use for the carbon so somebody will actually buy it. Do you guys, either of you, work in that area as well?
So we do a lot of, we do some work in carbon use, but the bottom line is the amount of, if we really go to full capture, 90% capture of power generation, there's probably not going to be enough use for the carbon in industry today. So you have to find other things to do with it, which is part of the reason things like the element cycle are so interesting, because they provide a use for that carbon to provide power, right? But I don't know if you have any perspective on that.
Well, no, I mean, from a pure volume perspective, it's the volume that is generated is going to overwhelm any individual use and in any sector. The one thing that it can do is if you can generate some kind of a revenue stream as part of your process, then that can offset some of the costs associated with capture. Now again, it's a numbers game, and the volumes associated are a challenge, but there are opportunities out there,
and that's an example where early adopters may actually have an advantage, because they'll be the first ones to that market, and that market's only so large.
I was really interested in that panel piece you're talking about. A lot of this is really in that basic research phase. What are some of the technologies that you're keeping around that make you really excited?
Well, so a lot of this is basic research, a lot of it is much further along, right? So I think what really excites us are the new and innovative cycles. I think that's really great. And I think the improvements we've seen in modeling capabilities, which allow us to really understand how different chemical solvents behave before actually going into demonstrations and pilot projects, is really going to help us accelerate that innovation and make sure we're investing our money in the right thing. So in the basic research space, I think understanding the chemistry and the thermodynamic reactions and getting really solid models is very, very important.
Thank you.
In terms of making sure that there's somewhere to actually store this carbon, is there going to need to be associated infrastructure investments in pipelines or other sorts?
Yeah, there is. There's no question. You've got power plants and industrial facilities all over the United States, all over the world, and the area. There are some areas that have really good storage capacity and availability. Some areas that don't have real great storage capacity. And so in order to understand how to handle all of that, you're going to need some mechanism to do it. And that's part of what I meant in response to one of the earlier questions was, if you look at these industrial sources, they create an opportunity to get that process started. If you capture from an industrial source and build a pipeline to send it to somebody who might want to use it, or somebody who might want to store it, that starts the process along in terms of getting right-of-ways and permitting and that sort of thing that is needed to build out a large system that is going to need to be place.
I'm sure there'll be a series later on storage, so I would recommend it when it comes to that, there'll be more information there.
Great. If nobody else has questions, I guess we're going to adjourn. Yes, it's correct. We're going to meet here again, not in this room, probably on the Senate side, on May 31st for the next carbon lunch, which will be on carbon storage in particular. And if you have any questions in the meantime, please don't hesitate to reach out to any of us. Thank you very much for coming.